We're going to talk about air resistance. This is something that we completely ignored for free fall, but we all know from personal experience that you often can't ignore air resistance, so we definitely need to address it. Air resistance is also known as drag. I define it as the force of a fluid on a moving object. In this example, you can see leaves falling from a tree, and for an object like that, drag is definitely important. You could not ignore drag in this situation. One property of drag is that it always points opposite the direction of motion. Well, that actually sounds a lot like friction, and indeed they share some similar properties. But one of the big differences, though, is drag specifically is force of a fluid on a moving object. If you remember friction, when we zoomed in to look between the two surfaces for friction, at a microscopic and atomic level, even really smooth surfaces are going to appear jagged. So it's the interaction of those jaggedy points where you get temporary bonds, and then those bonds get broken by the motion, and that releases vibrations into the atomic structure there. And so that's why you're losing motional energy and converting that into thermal energy or generating heat. So on the other hand, when I think of what it's like to experience drag, I always think of this. It's kind of like trying to walk through a ball pit. Have you ever had an experience to play around in one of these? It's quite difficult to move around. I like to imagine it like this. The skydiver here is feeling air resistance because they're actually moving through countless number of tiny particles. They're ramming into each one, and they physically have to push them out of the way. So that's what air resistance is at an atomic or molecular level. There's two principal factors that influence air resistance. There's more than the two, just note that these are the principal ones. These are the ones that cause the most influence. So the first one is speed. To give you an idea why speed is important, here's a car that's going to be driving through some air, and as it does, it's going to be colliding with these air molecules. At slow speeds, there's collisions, but they're relatively less frequent, and they're not going to have as big of an effect. You know, an individual collision with an air molecule really isn't noticeable. It's only when you consider the countless collisions that you're having that it starts to add up. Now, when you're going a lot faster, you can see that the collisions are going to happen at a much higher rate. So even though individually they don't do a lot because there's so many more per second, it really adds up and you start to notice the overall effect. The second factor I want to talk about is called frontal area, and this one's a little hard for me to show. But if this is our car, the frontal area is the two-dimensional area that's facing the direction you're traveling. So I can't show it quite as good here, but I'll imagine a side view. So from the side view, this would be the frontal area of the car. So as far as the air is concerned, it's almost like there's just the big square block here that's really causing all the air to get pushed out of the way. So kind of like this. Imagine as the car is going through its frontal area, it's just plowing all that air out of the way. Right, now you might be wondering, well, isn't that what aerodynamics is, to change the frontal area? And the answer is no. Aerodynamics is a different issue, and it is important. The shape of the object definitely plays a factor into the amount of air resistance it experiences, but it's separate from this concept of frontal area, and I'll mention that a little bit later. Okay, so to describe frontal area, we need to actually look at the front of an object that in the direction it should be traveling. So for a vehicle like this, the frontal area would be that two-dimensional outline. So this is the area that's going to be going into the wind or in the direction of travel. So if we added up this two-dimensional area, that would be the frontal area. And again, all the little curves and bends in the hood, and that's not frontal area. That is a factor, but it turns out to be it's not that it's not important. It's just doesn't have quite the same contribution. So let's do some thought experiments here. If I have my guy fallen flat like this, his frontal area is going to be the whole front side area that's facing the direction of his fall. If he were to instead fall feet first, then his frontal area is just that. So you can see that there would be significantly less drag in this case than this case. He's pushing less air out of the way, if you want to think about it that way. Okay, here's an example of frontal area and why it plays such a big role. Here I have a ping pong ball and a piece of paper. And we're just going to drop them. It's no surprise that the paper trailed behind significantly. It has a lot of frontal area compared to the ping pong ball. Okay, just because it's fun, we're going to watch that in slow motion. So the frontal area would be the 8.5 by 11 inches. In this video, what I did is I took the exact same piece of paper and I just crumpled it up into a little ball. So I've significantly reduced its frontal area. Keep in mind that the mass is exactly the same. It hasn't changed the weight of the paper in any way. So by changing the frontal area, you can see a significant difference in the fall. All right, last topic is known as terminal velocity. So again, I have my guy falling here. What is terminal velocity? That's when your falling velocity no longer increases. That's what we mean by terminal. It's ending. It's reached its maximum point. We now know that the connection between velocity and acceleration is that if you have a constant velocity, then you must have zero acceleration. So terminal velocity is zero acceleration. We also know now that Newton's second law shows us the relationship between acceleration and net force. And so if we have zero acceleration, we have zero net force. Let's look at the forces on my guy as he's falling. We know there's gravity, and there's obviously drag or air resistance. Those are really the only two forces at the moment. So if the net force is zero, and these are the only two, they must be opposite direction but equal. So we can add to our terminal velocity definition that terminal velocity happens when gravity is equal to drag. A little later, we're going to define gravity as mass times the acceleration due to gravity. So m for mass, g is the acceleration due to gravity, which is about 10 meters per second squared. We can define drag. This a is the frontal area. V here is the speed, and notice that it's squared, so that's why speed is so dominant in terms of the amount of drag you feel. If you triple your speed, you actually increase your drag by 9 times. This C here is just sort of a symbol that I'm using to encapsulate several different ideas. Hidden inside C is the density of the fluid you're moving through, also the shape of the object and how that affects drag. So that's where you would think of aerodynamics as kind of hidden inside C. We know that those should be equal to each other, so I just set them equal to each other. Now you notice I have a speed here that I can solve for, and this condition was set up assuming terminal velocity, or when drag and gravity are equal. So if we solve for v there, that's what we call terminal velocity. I'm not going to use this equation much in this class. I don't typically do a lot of the math at this level, but I mostly want to use it to point out two things. Okay, first of all, terminal velocity increases with mass. You can see that because the mass is in the numerator. It's not a one-to-one relationship. You know, if you double mass, it doesn't double terminal velocity, but at least we can say that it does increase. So if you add mass, you add terminal velocity, meaning you would be going faster at that terminal velocity. Frontal area, on the other hand, decreases terminal velocity. So if you increase your frontal area, it actually decreases the speed that you can achieve while falling. Okay, so here's a little question. Assuming these two figures have the same mass, which one has the greatest terminal velocity? Well, let's look at their frontal areas. So this guy would have about that, and he would have about that. From the relationship we derived, frontal area is sort of an inverse relationship, so more frontal area means less terminal velocity. So in this case, the greatest would belong to this guy. Okay, slightly different situation. Assume they have the same frontal area but different mass. Which one has the greatest terminal velocity? I'm assuming that the bigger one has more mass. And again, from that relationship, the more massive one should have the largest terminal velocity. If you think about it this way, the heavier the person is, the faster they have to fall to build up more drag. As soon as their drag can equal their weight, then they've hit terminal velocity. So the more weight they have, the faster they have to go for drag to equal their weight. Another one. Assuming they have different mass and frontal area, which one has the greatest terminal velocity? So there's the frontal area there, there's the frontal area there. Now, in this situation, I'm assuming this one has more mass and more frontal area. Problem is, those are competing terms. So more frontal area would slow them down, but more mass would speed them up. So to answer this question, we actually don't have enough information. We would need more specifics on exactly how much more frontal area this is than that, and how much more mass is here than there, before we could actually state that. So because they're competing, it kind of cancels out the obvious guess. Last question. These definitely have different mass. Now the parachute here, we're going to assume is the same area, same frontal area. So that frontal area factor is the same for both of them, it's just their mass. Assuming they start at the same height, which parachutist will reach the ground first? Well, the question is simply which one is going faster if they have the same distance to travel, and it's going to be the heavier one in this case.